But now let's get to calculus. Sequences in series, chapter 11.1 to 11.7. Luckily for you, we made an acronym, PD Dart Girl. P for P-series, D for divergence test, DCT, AST, ratio, telescoping, geoseries, integral, roots, and LCT. Okay, so first we're going to do number 8 from the worksheet, and number 8 is the sum of 1 to infinity for n to the power of negative 345.9. And then the first step is to transfer that into the fraction form, and once we do that, we can see that it's in the P-series form. So this is going to be about a P-series. So since P equals 345.9, which is greater than 1, and it's in the format 1 over n to the P, it converges. But if P was less than or equal to 1 in 1 over n to the P, then it would diverge. And some of the common mistakes that students make is that they think it's n to the P instead of 1 over n to the P, which is the reciprocal. And the big one is also be careful simplifying, because that's where little mistakes are made. So next we're doing number 4, which is the sum of 1 to infinity of 17 to the n plus 4 to the n over 2 to the n. And then the first step we can do is to simplify that equation, which puts 2 to the n over each part, which gives you 7 to the n over 2 to the n plus 4 to the n over 2 to the n. And then we can combine into like fractions because they have the same exponent, which gets you 17 over 2 to the n plus 2 to the n. And we can take the limit of that as n approaches infinity, which gets you infinity plus infinity, which doesn't equal 0. So this is like, since we took the limit of n to infinity, it's the divergence test. So since the limit as n goes to infinity of the sum of 1 to infinity of f of n does not equal 0, then by divergence test, it diverges. And if the limit of n to the, as n approaches infinity of the sum of 1 to infinity of f of n equals 0, then you have to use another test in order to determine if it converges or diverges. And the common mistake that students do is that they prove convergence by divergence tests. So remember that divergence test only proves divergence.
Yeah.
So we're going to do number 10 now, which is the sum of 8 to infinity of 6 over square root of n minus 7. And for this one, we're going to use DCT. So by using DCT, we have to compare it to another sum, and in this case, we're going to compare it to 1 over n to the 1/2. And to find which one's bigger, we see that square root of n minus 7 is less than square root of n. And if we take the opposite or flip it, then the signs also flip. So that makes 1 over square root of n minus 7 bigger than 1 over square root of n. And we bring that back to the original equation, and that makes our original sum greater than the sum of 1 over n to the 1/2. And since we know that 1 over n to the 1/2 diverges because of P-series, since that's the one we just learned, we can know that the new sum also diverges by DCT now, since it's greater. And some common mistakes is comparing correctly. So when we use DCT, we want to always see the smaller one should always diverge and the bigger one should always converge. So now we have number 15, which is the sum of 1 to infinity of negative 1 to n minus 1 over n minus n to the 2/3. And when we first see this, like we see this negative 1 to the n minus 1, that should be like a red flag for us to know that this is going to be an AST problem. So the first thing we have to do is prove that the n plus 1 is less than the original equation. So we have 1 over n plus 1 minus n plus 1 to the 2/3 is less than 1 over n minus n to the 2/3. And that is true, so we have a little check there. And then we take the limit as n approaches infinity, and if that equals 0, then that is convergent by AST. Now we have to prove if it's conditional convergency or absolute convergency, and how we do that is taking the absolute value sum and comparing that and see if that's divergent or convergent. And when we do that, we get 1 over n minus n to the 2/3, and we use DCT and compare that to 1 over n, and since 1 over n is a harmonic series, we can find that our original sum diverges. So that makes it conditionally convergent. If this sum was convergent, then it'd be absolutely convergent. And some common mistakes is that students don't check for absolute or conditional convergency. Okay, so now for number 3, we have the sum of 1 to infinity of 2 to the n plus 3 times n plus 7 factorial over n plus 11 factorial. And these factorials are like a red flag for the ratio test, which is over there. So what we do for the ratio test is we take the limit as n approaches infinity of n plus 1, of wherever we see an n, you just add 1 to it. So factorials would be 2 to the n plus 4 times n plus 7 factorial times 1 next term, which is n plus 8. And do the same thing at the bottom. And you multiply that by the original equation. And that gets you to the times n plus 8 over n plus 12. You take the limit as n approaches infinity, it gets you 2. And some common mistakes is basically just to know the rules. So if your output is greater than 1, it diverges by the ratio test. If your output is less than 1, it converges. And if your output is 1, then it's inconclusive, and you have to use another test. Now we have number 6, which is the sum of 1 to infinity of 3 over n squared plus 5m plus 4. And what we want to do here is use PFD. So we set up our equation there, and then we plug in our wanted values for a and b, and we get our outputs as 1 and negative 1. So we get our equation is the sum of 1 to infinity of 1 over n plus 1 minus 1 over n plus 4. And then now we plug in the n, so 1 to infinity, and then we write out the sum. And that gets us 1/2 plus 1/4 plus 1/3, because we can see that these cancel out, each of these terms start canceling out. It converges because we can see that there's a sum. We also have to note that the last term is 1 over n plus 1 minus 1 over n plus 4, and we take the limit of those, and those both give us 0. Some of the common mistakes is forgetting about those infinite terms. So sometimes they don't go to 0, and to tell if they go to 0 or not go to 0, we take the limit as n approaches infinity. So now we're going to do a geoseries example. Our example is the sum of 1 to infinity of 2 to 3n over 27n. And we can rearrange that fraction into 8 over 27 to the power of n. And since x, which is where we have here, equals 8 to the 27, then that's less than 1 in x to the power of n. That means it converges. If x was greater than 1, then it would diverge. And then we would take the common ratio of 8 over 27 and plug that into our sum equation, which is the first term divided by 1 minus the common ratio. So for us, it's 8 over 27 divided by 1 minus 8 over 27. And that gets us 8 over 19. And some of the common mistakes is just forgetting this summation formula. So now we're going to do number 5. And it's the sum from 1 to infinity of n to the power of 5 times e to the power of negative n to the power of 6. And since we can see that there might be u sub involved, we're going to use the integral test. And when using the integral test, we have to state the criteria, which means that the sum is positive and it's decreasing. So the first step is to set up the integral, and we don't really want the infinity at the top, so we're going to use t instead. So we use the limit as t approaches infinity. We do a u sub. That gets us right here, where the limit is t to infinity of negative 1 over 6 times e to the t minus e to the 1, and that gets us infinity. And since the integral diverges, then the sum also diverges. And the common mistake is that people will forget that this criteria. If you don't state that, then technically you can't really use the integral test. And also, if it did converge right here, that's not the sum, because remember, you can only use the sum, you can only find the sum by using telescoping in geoseries. So now we're doing number 9, which is the sum of 1 to infinity of 2 to the power of 2n plus 2 over 4 to the power of n plus 3, all to the power of n. And when we see like everything to the power of n, that should like trigger something in our mind, tell us roots test. So what we're going to do is we're going to start applying roots test, which we make n approaching infinity, and we take the nth root of the original equation. And that gets rid of the n, and that gets us to that equation. And then we take the limit, and that gets us 1 over 2 to the power of 4, which is 1 over 16. And if the limit, our final output, is greater than 1, it will diverge. If it's less than 1, it will converge, which is right here, which means this sum converges. And if it equals 1, then the roots test is inconclusive. And some common mistakes is that most people forget these rules, so make sure you know these rules very well. So now we do number 2, and it's the sum of 1 to infinity of n squared minus 5 divided by the square root of n to the 7 minus 3n plus 13. And when there's square roots at the bottom, we usually want to use LCT. So we're going to make this original function, a of n, and we're going to compare it to 1 over n to the power of 3 over 2. And we get that because we take the highest powers, which is n squared minus n to the power of 7 over 2. That gets us n to the power of 3 over 2 right there. So we're going to do LCT, and we take the limit as n approaches infinity of a of n divided by b of n, and that gets us 1. So now, so this 1, we can now compare base with b of n. So our rule is if the limit as n approaches infinity of a of n over b of n is greater than 0 and finite, then it's based on the function of b of n. So we look at 1 over n to the power of 3 over 2, and that is convergent by p-series since p equals 3 over 2 and is greater than 1. And some common mistakes is just to know the rules of right here. So we want to know that if when a of n over b of n is greater than 0 and finite, then we can base it off b. So now we're going to talk about the remainder. The first part is finding the sum of the first x terms. So you make x your upper limit of the summation notation. So, and then you would plug into your calculator. This is usually a calculator question. And next would be how many terms you need to have an error less than y. You make y your remainder, and y remainder would be less than or equal to the integral of a of n. So you would make your function integral and solve from there to find the terms you need. And then you would round up to the nearest whole number. So if it was 17.1, you would round to 18 terms. So now for alternating series, you would, a sample question would be like how many terms need to have an error less than y, and for this one you would just make the error equal to a of n and solve for n, the number of terms. And for alternating series, we would round down. So if it was 17.9, we would round down to 17 terms. And a common mistake is confusing different types of errors and when to round up or down. So remember, a regular remainder is rounding up, an alternating series remainder is rounding down.